Ever worked with someone who is undeniably brilliant at their job, but an absolute nightmare to manage? They demand a massive paycheck, require incredible special treatment, and one wrong move sets them off. The periodic table actually has its own version of this high-maintenance VIP. It's element number 4, beryllium. As a raw material, it possesses physical properties that engineers dream about. It can survive environments and extreme pressures that would easily tear standard metals apart. Because of that unique resume, our ability to launch deep space missions or build cutting-edge defense systems relies entirely on keeping this incredibly difficult element in the mix. This visual scale shows exactly why engineers are so drawn to it. If we compare identical blocks of aluminum and beryllium, the scale immediately drops on the aluminum side. Aluminum is already famous for being light, but beryllium weighs even less, coming in at under 2 grams per cubic centimeter. But lightness usually comes with a massive penalty in strength. That brings us to the metal's most defining trait, its extreme resistance to bending. Watch what happens when heavy weights come crashing down on both blocks. The aluminum bows deeply under the pressure, while the beryllium block stays completely flat. It is actually 4 times stiffer than aluminum. That combination of being feather-light but nearly impossible to bend is rare. For aerospace engineers designing structures that have to survive the violent, rattling shaking of a rocket launch without warping a single millimeter, it is the perfect material. The requirements get even stricter once those structures reach the vacuum of space. Out there, materials are exposed to wild temperature swings. Most metals expand in the heat and shrink in the freezing cold, but beryllium barely reacts to those extreme changes. When NASA designed the $10 billion James Webb Space Telescope, they needed a massive mirror that would hold its exact shape out in deep space. That giant yellow honeycomb structure you see being assembled here is made of beryllium. When you are putting something in orbit, a bent frame or a slightly warped lens ruins the entire mission. You need a material that refuses to flex while weighing as little as possible. Beryllium easily wins the job. If this metal solves so many engineering problems, it makes sense to ask why we don't build smartphones or everyday cars out of it. This brings us to the first major hurdle of working with our VIP element. When it is handled, cut, or sanded down in a workshop, it becomes highly toxic to humans. Machining the metal creates a fine dust. If a worker inhales even a microscopic amount of that dust, it can trigger chronic beryllium disease, a permanent and severe lung condition. Because of this hazard, factories cannot simply run it through a standard assembly line. Facilities require intense medical monitoring for staff, specialized ventilation systems, and workers operating in bright yellow hazmat suits and full-face respirators just to shape a single part. The sheer cost of protecting human lungs from this dust adds an enormous premium to the manufacturing process. It forces companies to reserve the metal only for projects where absolutely nothing else will work. The headaches start long before the metal reaches a workshop. Getting the raw ore out of the ground in the first place is a slow, difficult process. Taking that rocky ore and isolating the pure metal requires a highly complex chemical process. The technical difficulty is so steep that the vast majority of the world's supply is refined by just 3 countries: the United States, China, and Kazakhstan. That massive bottleneck drives up the price. Before a single piece is even molded into a useful shape, the raw material alone can cost hundreds of dollars per pound. You also can't go online and buy it on a massive public commodity exchange like you can with gold, copper, or oil. Sales are negotiated privately behind closed doors between the few refiners who make it and the industrial buyers who desperately need it. Because the trading pool is so small, the market is incredibly sensitive. A single large order from an aerospace company can instantly cause the price to spike for everyone else. You have a material that is dangerous to breathe, heavily restricted by geography, and wildly expensive. The result is one of the most fragile supply chains on the planet. The U.S. Department of Energy monitors this exact fragility. Because the element is so difficult to source, but completely necessary for advanced technology, they officially classify it as a critical material. This metal is a requirement for high-stakes hardware. The military relies on its extreme heat resistance and low weight to build missile guidance systems and the delicate electronics inside advanced stealth fighters like the F-35. This diagram shows the true geopolitical risk. If a single major refining plant goes offline due to an accident, or if international trade with China snaps, the parts required to build national defense systems would quickly dry up. Engineers are trying to replace it where they can, swapping in materials like carbon fiber composites for certain structural parts. But when you look at the most demanding military and space environments, those alternatives still fall short of beryllium's raw physical performance. The threat of losing access is taken so seriously that the U.S. government actively provides financial support to keep domestic refining facilities running. They are paying to ensure the country always has a local supplier. The next time you watch a rocket clear the launch pad, or see a crystal-clear photograph beamed back from 1 billion miles away, you'll know exactly what it took to get it there. It was built on the back of the most talented, difficult, and high-maintenance element on the periodic table.